Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss about the method of undetermined coefficient for non-homogeneous linear differential equation part 2. In the first part, we studied about the method of undetermined coefficient when Rx is not belongs to basis of YC. Here, we will discuss about method of undetermined coefficient when Rx or any part of Rx lies in basis of complementary functions YC. Here we first recall the last method of undetermined coefficient. Here our differential equation is fn d raised to ny up to f2 d square y plus f1 dy up to f0 y rx, where rx is not equal to 0 and it is nth order non-homogeneous differential equation where f1, f2, f0 and fn are constants. D by dx is differential operator. Now we find the general solution of differential equation and it depends on Rx and Yc complementary function. It is obtained by y equal to Yc plus Yp. In the method of undetermined coefficient, we can apply this method for some special functions like exponential, trigonometric sine and cos, and algebraic function and its special type of polynomial. Now, this method is applicable also for linear combination of these above functions, and also it is applicable for product of these above functions. Here, the choice of Yp depends on complementary function. Here, last time we see the first case of method of undetermined coefficient. Here, we will recall it. First case of undetermined coefficient is when Rx is not belongs to in basis of complementary function, then it is choice of Yp is obtained from this table where Rx is constant, then Yp is only undetermined coefficient k. We can find its value by differentiating Yp and put in differential equation and compare with the right hand side function. If it is Rx is algebraic function or any polynomial, then Yp is kn x raised to n plus kn minus 1 x raised to n minus 1 up to k1x plus k0. Here kn, k1, kn minus 1 all are undetermined coefficient. We can find the value of it by method of undetermined coefficient. If Rx is e raised to bx, then choice of Yp is k e raised to bx. If Rx is only cos ax or sin ax, but in the choice of Yp, we will take the always linear combination of cos and sin both. Here Yp is a cos ax plus b sin ax. A and b are undetermined coefficient and they are calculated by method of undetermined coefficient by differentiating Yp, Yp dash, Yp double dash and put in the differential equation and compare with right hand side function. Here if Rx is a linear combination of e raised to bx and cos ax, or it is a linear combination of e raised to bx and sin ax, in this case choice of Yp depends on both type of functions exponential and sine and cos. Therefore our choice is Yp is equal to k e raised to bx plus a cos ax plus b sin ax. In this case, we apply the linear combination of exponential functions as well as cos and sine. Here, if Rx is a linear combination of all three types of functions, that means e raised to a bx plus cos ax plus x raised to n, or Rx is e raised to bx plus sin ax plus x raised to n. In this case, choice of Yp is like k e raised to bx plus a cos ax plus b sin ax plus kn x raised to n plus kn minus 1 x raised to n minus 1 up to k1x plus k0. Here a1, here k1, k2, kn all are undetermined coefficients as well as k, a and b also are undetermined coefficient. Here all the undetermined coefficients are obtained like this. First of all, find the Yp, Yp dash, Yp double dash in the terms of undetermined coefficient and put in the non-homogeneous differential equation and compare with right hand side function Rx and find the value of undetermined coefficients. and put in choice of yp. So we get the particular integral according to the table. Now general solution is obtained like this: y equal to yc plus yp. Let us see the case number 2, in which Rx lies in the basis of Yc. Here Rx or any part of Rx lies in basis of Yc. So we find the choice of Yp according to this table. If our function Rx or any part of Rx belongs to basis of Yc, then we multiply particular integral with x, x square, x cube, etc. according to the example. Here Rx is x raised to n, that means that it is algebraic function, and Rx is equal to x raised to n belongs to choice of Yc. Then choice of Yp is equal to x into kn x raised to n plus kn minus 1 x raised to n minus 1 up to k1x plus k0. Here kn x raised to n plus k1 x raised to n minus 1 up to k1x plus k0 is a choice of x raised to n according to the case number 1. But here our Rx x raised to n belongs to complementary function, so we multiply it by x. If Rx is e raised to bx and e raised to bx belongs to basis of Yc, as well as x e raised to x also belongs to in basis of Yc. In this case, Yp is equal to k times x square e raised to bx. Here e raised to bx belongs to Yc, as well as x e raised to bx is second time belongs to Yc. So Yp is equal to k times x square e raised to bx. Here k is undetermined coefficient. If Rx is cos ax or sin ax and they are belongs to in Yc, then choice of Yp is x into a cos ax plus b sin ax. Here if cos ax and sin ax second time belongs to in Yc, then again we multiply with x square, then Yp will be x square a cos ax plus b sin ax. So that means when our function Rx or any part of Rx belongs to basis of Yc, then we multiply with our choice of Yp by x, x square, x cube up to so on according to our Yc basis. Now we will find the Yp, Yp dash, Yp double dash and put in the non-homogeneous differential equation and compare with the right hand side function Rx. Find the value of each undetermined coefficient and put in Yp. That is our proper particular integral according to the Rx. Now our general solution is y equal to yc plus yp. So this is the case number 2, when Rx or any part of Rx belongs to Yc, then we multiply our choice by x, x square, x cube up to so on according to the basis of Yc. Now let us see some example related to this case. Here d square y by dx square minus 6 dy by dx plus 9y equal to 18 e raised to 3x. Now first of all we find the corresponding homogeneous differential equation in the differential operator form. D square y minus 6 dy plus 9y equal to 0, where d is the differential operator, d by dx. So our auxiliary equation is d square minus 6d plus 9 equal to 0. It is a perfect square. So after factorizing we get the factors d minus 3 whole square equal to 0. So our auxiliary roots are real and repeated and they are 3. So y1 is e raised to 3x and y2 is x time e raised to 3x. So our yc is c1 e raised to 3x plus c2 x e raised to 3x, where c1 and c2 are arbitrary constant. We will apply the undetermined coefficient method to find yp. Now Rx is 18 e raised to 3x. Bases of Yc are e raised to 3x and x e raised to 3x. Here Rx belongs to basis of Yc, as well as x e raised to 3x is also belongs to basis of Yc. So our choice of Yp is a x square e raised to 3x, because e raised to 3x is also belongs to basis of Yc, as well as x e raised to 3x is also belongs to in basis of Yc. So we have to multiply our choice of Yp by x square. Now how to find the yp in this case? Let us see by calculating. Here y double dash minus 6y dash plus 9y equal to 18 e raised to 3x, which is our non-homogeneous differential equation. Yp is equal to ax square e raised to 3x, because our Rx is in basis of Yc. Now Yp dash equal to 2ax e raised to 3x plus 3ax square e raised to 3x. Now Yp dash can be written like this: 2ax plus 3ax square e raised to 3x. Now we will find Yp double dash. Yp double dash equal to 2a plus 6ax into e raised to 3x plus 2ax plus 3ax square. Derivative of e raised to 3x is 3 times e raised to 3x. So this is our yp, yp dash and yp double dash. Put yp, yp dash, yp double dash in differential equation and compare with Rx. But here we have only 18 e raised to 3x. We don't have a x e raised to 3x and x square e raised to 3x on right hand side. So we will compare with only 2a e raised to 3x. Therefore, we have a 2a e raised to 3x equal to 18 e raised to 3x. Now cancel e raised to 3x from the both side and 2a equal to 18. Therefore, a will be 9. Now put the value of a equal to 9 in yp and we get the particular integral yp equal to 9x square e raised to 3x. So our general solution will be y equal to yc plus yp, where y equal to c1 e raised to 3x plus c2x e raised to 3x plus 9x square e raised to 3x. That is our general solution of our differential equation d square y by dx square minus 6 dy by dx plus 9y equal to 18 e raised to 3x. Here we apply the second case of undetermined coefficient method because our Rx equal to 18 e raised to 3x lies in our basis of Yc. Now in the next lecture we will study about the case number 3. Thank you very much.